In this lesson, you will be introduced to rational functions and rational expressions. A rational expression is an expression that can be written in the form p over q, where p and q are polynomials and q does not equal 0. The way a rational expression could differ from a regular basic fraction is that you may have variables in the numerator, denominator, or both. And so because of that, we run the risk of the value of a denominator going to 0, which is why the statement q cannot equal to 0 is written. A rational expression is simplified when the numerator and denominator share no common factors. Simplify the rational expression in the first example. Completely factor the numerator and denominator, then divide out common factors. So let's look at our first example there. We have 7 over 21a minus 77. If I want to simplify this fraction, I first need to see if there are any common factors. And to find common factors, we actually factor. Now 7 does not break apart because it's a prime number, but 21a minus 77 has a common factor of 7 in it. And so if I factor that out, I get 3a minus 11. And then you can see there that we have a common factor of 7 in the numerator and denominator. Now these will divide out. 7 divided by 7 equals 1. And so that tells us that our final answer is 1 over 3a minus 11 for the simplified fraction. Looking at the second example, I want to check to see if this has any common factors, and the way I do that is I actually factor. Notice that the top is a trinomial that starts with a 1. That means we can use the factor pair shortcut for factoring. Remember how that works. For x squared, we do x times x, and then we're looking for the factor pair of 6 that multiplies for 6 and adds for 7. And that would be 1 and 6. So we'll say plus 1 plus 6. And in the bottom, there's a greatest common factor of x. So I'm going to factor out that greatest common factor, and I get x plus 6. Now I'm going to divide out the two binomial common factors. Factor divided by itself is 1. And then on the top, 1 times x plus 1 gives us x plus 1. And in the denominator, we're left with x. Now this is the final answer. Those x's do not divide out because the x on top is part of the binomial x plus 1. That is a factor itself. And then the bottom, the x is its own factor. So only factors divide out, terms do not divide out. So that would be the final answer there. In the last example, we can see that we have a difference of 2 cubes on the top. And remember how that would work. We would say, okay, what do we cube to get each of these? And x cubed, you cube x for x cubed, and 1 is cubed for 1. And remember how the factorization works. It's a binomial and a trinomial. In the binomial, remember we pick up x minus 1. In the trinomial, we do x times itself, x times 1, and 1 times itself. And then remember the signs. If you have minus, this one will be a plus, and this is always a plus. In the bottom, we have something a little bit more complicated, and I'm going to kind of make some room here to show this work. We have a 4-term polynomial that needs to be factored, and remember we would do factoring by grouping when we do that kind of a problem. So what I would do is take 5xy plus 7x minus 5y minus 7. I'm going to kind of work off to the side here. In the first two, we have x in common, and we get 5y plus 7. In the second two, I don't see a number in common, so I'm going to use a 1, but I'm going to use a negative 1. Remember how we would do that? And when I divide by negative 1, I get 5y plus 7 for the remaining two. And then that's going to give me 5y plus 7 and x minus 1 as the two factors for the denominator. So I have 5y plus 7 and then x minus 1. You can see that the x minus 1s are the common factors. They divide out. And this leaves me with x squared plus x plus 1 all over 5y plus 7 is my final. So let's move on to the next idea, which is rational function. A rational function is a function that contains a rational expression. So f of x equals p over q. The rational expression is p over q. And a lot of times we're being asked to evaluate. When we evaluate a function, it means to find the value of the function at the given x value. So for instance, look at this example, evaluate f of x equal to x minus 10 over x minus 5, and they're saying f of 12. Well, that means the x should be 12. So if I take this original function here, what I'm going to do is I'm going to say, okay, I'm doing my function, I'm going to plug a number in, and I'm plugging in the number they tell me to. And in this case, the number they tell me to plug in is a 12. So I'm putting a 12 here and here. And then this is going to give me my final answer, which 12 minus 10 is 2, and then 12 minus 5 is 7. 2/7 would be the final answer on that example. In the next example, they again want us to use that function, but they want us to plug in a different value for x. So if we plug in what they're telling us to, the 0, okay, we're going to get on top negative 10 and bottom negative 5. Those evenly divide out for positive 2. So that would be the final answer on that one. For f of 10, they want us to use our function again, but this time they want us to plug in 10. So we can do that. We'll say 10 gets plugged in wherever x is. And then notice that we get 0 on top. This is a 10 right here. Kind of looks weird. 5 on the bottom. 0 divided by 5 is 0. And then on this last one, again, using the same function, they want us to plug in the number 5. So we will. So I'm going to plug in 5 on top and 5 on bottom for this one. And something interesting happens here. We get negative 5 in the top, but we get a 0 in the bottom. Now remember that division by 0 is what we refer to as undefined. And the reason it's undefined is the way division is defined off of multiplication. What they're asking us to find is this. What number, when multiplied by 0, gives us negative 5? Well, there isn't one. That's why this is undefined. If you want to see that example used here, what number, when multiplied by 5, gives you 0? And the answer is 0. That's why there is an answer for this example. Okay, the domain of a rational function is the last topic for this lesson. The domain, which we often indicate with a capital D, is every value of x, or the input variable that, or every value that x is allowed to be, or that x, or the function is defined for. We use this very formal notation here. D stands for domain, and then we use that little kind of curly notation of brace. X is the input, and then there's a vertical line that means such that in math, and then it says x is a real number. Generally, we're going to say that most domains are x is a real number, meaning pretty much anything plugs in. Sometimes, though, we run into numbers that cause us problems, and that's what this second part is about, and we'll talk about when there is a problem. It says to find the domain of a rational function, determine if there are any values that cause the denominator to become 0. Remember earlier we talked about how we don't want a denominator to be 0 because it makes things undefined. So since dividing by 0 is not defined, we have to exclude those values from the domain. So when is this going to be an issue? It's going to be an issue when there's actually a variable in the denominator. So you see here, there's no variable in our denominator, no variable. That means we're never going to have a 0 in the bottom of that because it's always just going to be 7. Now we could get a 0 on the top, but we're always worried about the bottom going to 0 because dividing by 0 is undefined. So when we give the domain here, we're going to say our domain is given by our input variable x, okay, such that x is a real number. And that's all we're going to say there because we don't have any numbers to worry about in this example. Now when you go to the next one, notice there's a variable down there. And so what we're trying to figure out is, okay, how do we know what makes the bottom go to 0? We take the bottom and set it to 0 and solve for the variable. And it actually tells us, oh, x equals 5 is the problem. So what we're going to say is, okay, our domain, the input is x. And x is going to be a real number when we do domain, real number. And this time, though, we have a problem. We don't want x to be 5. So that does get added in on that problem. In the last example, notice again in our denominator there's a variable, the x squared has the x variable. So if we want to solve to figure out what values are going to give us a problem, we take the bottom, set it to 0. This is x squared is going to have 2 solutions, or we expect to. And this is going to give us a difference of 2 squares. Remember, x squared is x times x, 36 is 6 times 6, and then we do a minus and plus, and this gives us 2 equations to work with for the values of x. Whoops. So this first one is going to give us a 6, the other is going to give us a negative 6. So there are actually 2 numbers that will cause us to go to 0 in the bottom. So when we describe our domain, we're going to say, okay, our input is x. X is a real number is kind of the fancy way of saying, look, pretty much everything works for x. Except for, we do have to be worried about negative 6 and 6. And then I'll close that off. And so this is the lesson that is Introduction to Rational Expressions and Functions. We talked about how to simplify a rational expression by using factoring and dividing out common factors. We talked about evaluating rational functions by plugging in values to the rational function. And then finally, we talked about domain, which really tells you the numbers that work for the function, and then also describes for you those that don't.